Okay, thanks everybody for logging in and attending this month's Design Professionals ABU Online. The topic is bioretention ponds and obviously considerations for retaining walls. Again, my name is Chad Julius, been with Allen Block for almost 19 years, and over the years we definitely are starting to see an increase in demand for these bioretention ponds, and by therefore we get more questions in our office. And so with that, we put a little presentation together with our production partners, giving them some information. We felt like it was pretty pertinent for the designers. This is not going to be a full 1 hour presentation, so it doesn't count for any continuing education credits, but it's pretty direct and to the point and things to consider. I do want to mention to everybody that you are on a listen or in a listen only mode right now. So if you do have any questions or comments, I would encourage you to use the question feature within GoToWebinar, and I'll be looking at those, but I also have a colleague, Don Clayton, online as well here that will be answering those as he sees them as well. And if I see one, I might read it out loud so everybody can get the question as well. So please participate as we go through this. But I do have just some simple objectives, and hopefully you guys can see my screen and as I advance these, but the objectives are pretty simple. We're just going to define what retention and bioretention ponds are. We'll talk about how retaining walls are impacted by these systems. And then obviously it always comes back to water management. In fact, just about every presentation we give for retaining walls, we talk about water management in some way, shape, or form. So to get started, I want to just kind of define and highlight what the difference between a detention basin or detention pond and a retention pond is. And it's kind of in the name. I've always kind of referred to as detention ponds. You're kind of detaining the water. So you're just temporarily holding it before it's discharged. And that discharge is always through kind of a single point source or through a pipe. So like you're capturing that extra capacity of water, but it's still being discharged in one location. You got that impermeable base, so it can't seep down. So you are really confining that or detaining that. Obviously, there are engineered controls for overflow and stuff in most of your pond applications. And that holds true for your retention. Retention, what you're trying to do is you're retaining that. So you're in fact holding it, and the goal is to actually recharge the groundwater reservoir, the aquifer below grade, so you're hoping that seeps through and into your groundwater source. Again, you still have your engineered overflow practices that need to come into play. So those are kind of detention and retention characteristics. Obviously, we're talking about bioretention ponds, and they go by a lot of different names. I've over the last couple of years, we obviously talk about them as bioretention ponds, but we also see bioretention swales and basins and cells. I've even heard people talk about them as rain gardens, and I don't know if that's exactly the case. I hear a lot of architects talking about that too, but it's an engineered solution for stormwater management. And really, I grabbed this. I listened to a presentation on the website, and it was I'm giving the guy reference here, a couple years old already, but I thought this was resonant to me because when I always think of bioretention ponds, I think of a pond. I think of stagnant water, something that's going to be there. But obviously, bioretention is not that. It's supposed to seep through there. In fact, most of the time, it should be relatively dry. So it's not that wetland. It's not that swamp. I kind of laughed at this. He's from Omaha, but we living here in Minnesota. We always say the mosquito, which is that biting insect, is kind of like our state bird in the summer. They get to be pretty big and pretty nasty around here. But obviously, if you don't have those water sources, you don't have the breeding ground for the mosquitoes. And it's not just a landscape bed. In fact, most of the public would probably just assume that's what they are. They'll walk right past it and not even realize that it's an engineered solution. But it is more than just that landscape bed. And then, of course, bioponds, biogardens, bioswales. It's a bioretention. It's retaining that water. And really what that bioretention process is, it's where the sediments and the contaminants that are being removed from the nearby runoff surfaces. So your paved surfaces, maybe your rooftops, but either way, you're introducing that water into that bioretention area. And what it does is it captures that polluted water and actually treats it. And so it takes those sediments and contaminants and I would say total suspended solids or the material from that water, and it gets captured within the media and the sand and stuff like that. And then it discharges it into your aquifer, and it's supposed to be cleaner. So you've got layers associated with this bioretention, and usually has some type of a grass strip, or maybe some riprap to slow the water down, some bedding sand. Obviously, they're organic material because you're growing plants and stuff in. So there's a lot more than the green grass or the green material that you see on top. In fact, on the picture on the right, that's what we see a lot. Most people would walk right past this, not even realize it's a designed, engineered solution for that additional stormwater that might be introduced because of a development or renovation. On the left, we get into a few more details where you see, obviously, you have that plantable material on top, but then you have that bioretention soil media. This media right in through here that's actually acting as most of the filter. Typically, you'll have some type of a sand layer here to keep the media coming down into your drainage rock. Your underlying drain, that depends on the application. You may or may not have that. If your subsoils are to the point where it'll accept it at a reasonable rate, you might not even have an overflow drain or something of that nature. Here's another detail, and I like this one because it kind of breaks it apart here, where you've got that water source coming from that stormwater runoff. You might get some temporary ponding because of the introduction of the volume of water, but eventually that all seeps through your soil media, through your sand, and into your drain rock. And this piping is going to be dependent on your design requirements. Here, they must raise the pipe up because they're looking at that additional capacity, storage capacity of that drain rock. So they'll let that fill up even before it hits their inlet pipe, outlet pipe. They're always going to have some type of an open throat catch basin. That's going to be a way to monitor and have that overflow protection as we go through this. So a lot of different ways a bioretention pond can look, but they're always going to come into those basic elements. Where those are, the depth of those, or how they're positioned, will depend on the design. But we know the benefits. There's a reason why you guys as engineers are getting asked to do more of this stuff. Let's face it, you're doing a lot of redevelopment or increased land use, and so now you got more impermeable surfaces that you got to worry about that additional watershed. And we know, and this is from the American Landscape Association, where you look at if you had like a 13-foot or 4-meter wide bioretention swale or bioretention pond, that's going to reduce the total runoff by almost 75%. So you're only going to get 25% of that total runoff. And that's quite a bit. So if you can have it go into your system and capture it, now you've got less runoff that you've got to worry about going to your neighbor's property or handling and satisfying the permit requirements for the land development in the first place. We also know we're doing a good thing with the environment, right? We're grabbing that water and we're reducing the pollutants. So the bioretention is going to remove that the particles. They're going to remove the grease, the grime, the stuff like that, and filter that through the soil media. That way you can recharge the groundwater. And it all comes back into that limiting the damage that you do. So kind of the LEED program. So you're looking for sustainability, stabilization, that kind of stuff. So anything you can do to help kind of improve your development is a good thing. So here's a couple applications I just grabbed from different manuals or different websites that I saw, and here's a great one where you can just see you've got some type of a paved surface, and that water is going to be introduced, and it's going over some rocks to kind of take out some of the major garbage, but slow that water down so you can minimize that erosion. But then it's being introduced into your pond. And so now you've got your soil media, you got your vegetation, you've obviously got your monitoring points and your overflow. So you've got those elements associated with that bioretention pond. Here, kind of a little bit more of that bioretention swale. Again, somebody might walk right past this and not even realize the importance of this, but you can see you've got inlets at designated points for that parking lot, and that's going to be captured by that bioretention, ultimately going into some type of a collection system, maybe down into your subsurface or to that outlet pipe, but at a much cleaner and slower rate. So great application there. Here's another one right along a roadway, kind of getting into more of that swale and kind of a bioretention cell as well. So you got individual compartments, again, slowing that water down, getting your contact points so it can actually filter through your soil media and again into your aquifer. So a couple different applications, but where we see retaining walls, for example, on this one, you got slopes on both sides. Maybe you don't have the room to do that. So here's one where you have that retaining wall. And so you put a retaining wall on one side. It has to be segmental on one, but then they got a concrete wall against the roadway. But now you can have that bioretention swale or cell, however you want to look at it, and still be able to keep your space and limit your excavation. And that's kind of where my transition's coming in for. That's where we see retaining walls. For example, here, this was just a site plan that was in our office. We know there's going to be some type of a detention or bioretention pond here. And so they're using a retaining wall on one side so they don't have to have the entire slope. By limiting the entire slope, they keep the capacity where they need to handle that stormwater. And so it's a balance act. You need to know your site conditions, but you also need to know your site topography and realizing how you're going to kind of stack everything into one location. And that's where the retaining walls has always been. Retaining walls are providing usable land, and that holds true with the bioretention. Here's another application. You can see it's obviously during a rainstorm, so you've got the slope that would be coming down, and the retaining wall is now holding back that slope, giving you the option to build that bioretention pond here. And obviously in the peak of a storm, you might see some obviously hydrostatic or saturated conditions, even some ponding water here. You can see it's coming up and over a lot of this plantable material, so there could be standing water. And so it always comes back to understanding the water. I mean, everything we do. I mean, there probably isn't a retaining wall course that we offer that we almost don't talk about water management. And depending on which expert you talk to, I've heard people say that most of your failures for water is because of water. So it might be 90% or even up to 70%. So it all depends. But we just know the vast majority of problems associated with retaining walls are because people are not handling the water properly. And that just compounds when you know you're going to have a bioretention area and how that's going to handle. So let's get into this a little bit. First, you understand what kind of volume of water you're going to have to deal with. And every site requirement might be different. You might be looking at, trying to account for your water quality, or it might be the water quality. When you're talking about quality, you're talking about, okay, how much soil media do I need? How much is it going to take to filter through that? And how much of the contaminants am I going to be able to remove? Where you're talking quantity, you're talking what is the size that I need? How big does that pond need to be? And it's all based on the amount of water. And that's going to be up to your local code, your local requirements. Again, I live here in Minnesota, so I just went to Minnesota and I did a little research, and boy, Minnesota Stormwater Manual has a whole section on bioretention requirements and design, and Minnesota is not alone. I can go anywhere. I know I got some guys from New Zealand here. You can go anywhere and you can do some search and find out what are the bioretention requirements. They've been around for a very long time, and it really comes into what is the volume of water. For example, you might have to handle, the engineer might have to go through the design and handle the first six inches of a rainfall over a 24-hour period. So first you got to calculate what is that rainfall amount and what is that 6-inch volume going to be, because then that's going to have to be stored in some way, shape, or form before I can even start discharging or anything like that. So there are different requirements that you might have to store. There might be different requirements that you might have to get to a contamination level. So is it quality or is it quantity that's going to be controlling your design? And that's all going to be up to the site-specific requirements. One thing we do know, we know grades are important. You're going to have to move the water towards your pond. And that's all this is kind of showing. We know that you're going to have some depression into the area so you can divert that water through your filter media and ultimately through your system itself. So that's where we see retaining walls coming into play. They're helping you manage that grade. But I do want to talk a little bit more about this water and location. Since we know bioretention ponds could potentially have that standing water, by all means, we know they're going to have saturated soils behind this wall. And Anybody that is familiar with the retaining wall designs, and I know there's a bunch of you on this call and this webinar that have some experience, you should start kind of twitching a little bit when you start talking about handling saturated soils behind a segmental retaining wall. That is one of the biggest do not do's in our industry. We're trying to eliminate saturated soils. We're trying to divert the water out and around. We're trying to handle concentrated water sources. We're trying to make sure the groundwater doesn't fluctuate. We're doing everything in our power to make sure the water behind the soil behind the wall doesn't get saturated. So for that reason, you're going to have to, if you're putting some type of a pond, like a bioretention pond behind the wall, you got to give it some space. You got to give you enough room to go ahead and allow you to get your reinforcement in, allows you to build your wall and be able to divert that water around the wall and not be right behind. And so there's a text sheet. If you go to the GoToWebinar options that you have, there should be handouts. You can download these. I'll obviously include these in the follow-up email. We're just kind of giving some general recommendations that these should be located. If they're going to be behind the wall or on top of the wall, they got to be at least 100% back. And so we're just going to make sure if you got a 5-foot high wall, that bioretention basin better not be anywhere close within that first 5 feet. You got to give yourself some room. And here's a real life application. We had this come into our office, and you can see if you look real close here, the grades, I'll get my laser out here, and you can see the grades kind of moving up the wall, and now my laser pointer just kind of stopped right here. So we know this is the low side of the wall. Then you got your parking lot above, and all of this water is going to be handled by this bioretention pond. It's calling out bioretention pond right here, but notice where that retaining wall is located. It's actually retaining directly that bioretention pond. So here's a smarter move, and one of the things we talked about with the site civil engineer was, okay, can we have the retaining wall here and hold up the parking lot, then bring in your inlet pipes and stuff to your bioretention pond that's below the wall? Is that a possibility? How can we regrade some of this and look at that? Because if you look at the concept detail that they had, here's where the flow is coming from. It's coming right from this area. We've got some riprap and stuff that is supposed to slow the discharge down. This hatching right here is kind of showing the potential high water mark. And you got the overflow and everything in through here too, but they got the high water mark. So they're anticipating they could have up to almost a foot of saturated or standing water. Then they've got the mulch and your soil media. That's about 3 feet thick, and you got some sand, and then you got the granular material. So imagine if this has got a foot of water on top of it, all of this is saturated as well. And you can think if you try to put a retaining wall, an Allen block wall right here, the problems that are going to be associated with that. And so that's why we try to make sure your bioretention system is not located directly behind the wall, and it's got to be behind, at least 100% back, probably even more, depending on your space. The better answer is to have those bioretention ponds in front of the wall, and now you can follow the best practices that we've put in place back in 2015. We put a best practices manual together, and really Chapter 5 really highlights that. And this is our standard water application detail. Some of you guys are very familiar with this. And really when you talk about water applications, when I talk to designing engineers, the critical elements are, where's your watermarks? Where is your high watermark? And where's your low watermark? Well, your high watermark is the end-all be-all design consideration. And that holds true for your bioretention system. So as soon as you do a water application, what do we ask you to do? We ask you to get rid of all the infill soil and make it all clean stone. And notice that we bring in some type of an embankment protection fabric as well. And we're calling out that rock, that clean stone, we call it wall rock, and the embankment protection fabric needs to extend at least 1 foot higher than your high water mark. Yes, we see guys go all the way up. Yes, we see guys take that fabric and go horizontally so that way this material doesn't fall into this. But the critical element for me is making sure you get the little extra redundancy that you're 1 foot higher than whatever that high water mark is. All right? And that's really what we're pointing out with the bioretention. We know that the water is going to be present. So if the water is going to be present, we know that we're going to have water and application. Once we know that, then you got to adjust your rock depth or height and your embankment protection fabric with that 1 foot clearance. And then you'll see, again, in that text sheet that you can download, I will provide in the follow-up, we've got these details. So you've got your bioretention system. You might have that water here, like that, for example, that one was 1 foot. So you're going to have a water line here. Then we're just going to go ahead and make sure we treat this as a water application. You go 1 foot higher than that potential high water mark. So you have to understand where that is. What we're trying to do is most bioretention systems do not have what they call rapid drawdown conditions. It's not like the water is going to build up and then all of a sudden it's like flushing a toilet where all of a sudden it just disappears. We know it's going to be a slow and steady decrease, and we know the water behind the wall needs to come down too. So water in front, water behind, that balances. The hydrostatic pressures kind of balance. So as the water comes down, the water behind the wall needs to come down as well, and that gets into this toe drain. That gets into making sure your drain pipe is at the path and providing that path of least resistance. So we try to get it down into your drain rock right away and below your planting media. Right? That way it can vent out just like we want it to, and it will never get trapped behind the wall. And notice some of the other things that are in here that I really want to point out is once you understand the height here of your high water mark, now it gets into embedment. How much block do you bury? Well, if you're familiar with bioretention systems, you know that planting media very often gets replaced. They will have to dig that out and replace it. So that way the efficiency of the system will continue. If this gets clogged, now all of a sudden you will see more and more ponding water on top. So they'll come in and replace this. Well, if this is going to get replaced, that means I got to get my block buried below that so we don't take that planting media as part of our embedment depth. We look at it from the sand and the drainage layer below. That is kind of like our finished grade now. That is where we're going to bring our standard embedment from that point. So our every wall height in a foot, we bury that much an inch. We're just going to go ahead and make sure we bury enough block so that way we're not going to undermine that structure. And that holds true for regardless of the size of the wall. Here's a gravity wall, same application. We're going to bury enough block, smaller a wall, doesn't matter. We're going to just make sure we bury the block, bring the pipe in, get that pipe into your drainage zone right away, not and below the soil media. I didn't point it out in the last detail, but that last detail we still had embankment protection fabric in front here. That fabric is not impermeable. That fabric still allows the water to come in and out. It is really meant to keep that soil in place. So it's more of that almost like embankment protection is how I keep referring to it because that's what we see. But I've seen some engineers call it filter fabric, and that's what they qualify as well. So we kind of keep it as geotextile fabric, and then the final engineer can make a determination. The last detail that's in our text sheet talks a little bit more if some engineers want to kind of keep the bioretention pond independent of the wall a little bit more. They bring in some select backfill in between here, so kind of that crushed rock. And we say just give some general requirements. We want to go about a 2-foot width. We're going to do our standard embedment, but here's where that fabric would come in place. But if you do this, now the wall is kind of outside of that soil media and planting media, so you don't have the same concerns. Again, I would still try to vent that wall out because this could be some water table here. We still want to vent that wall out into your drainage area so it's still vented to daylight. So a lot of things to consider. If you noticed in that one detail or one picture, maybe some of you guys noticed that they did bring in some select structural backfill here, probably a little bit for erosion protection. So if the water comes in, it's not going to undermine that wall. So very simple a way to bring in some of that crushed rock as we go through. So any questions on some of the topics that we've covered so far? And please use that question feature in the GoToWebinar. And what I'm going to do is just kind of watch that, but then also present one of the projects we worked on actually in 2016. So here, this was a medical facility down in Fayetteville, Arkansas, Washington Regional Medical Center. They did a 100,000 square foot or 9,300 square meter expansion in 2016. And obviously you guys are in the construction industry. Anytime you do an expansion, you're changing the water management requirements because now all of a sudden you got more impermeable layers of developed area, so you got to handle that water. So what they had to design a pond for was to handle the 100-year storm event, which kind of equated to about 15.25 cubic feet per second, or zero point 0.45 cubic meters per second. That's a lot of water in a short amount of time when you look at that 100-year event. So they had to look at it in a couple different phases. They wanted to size the pond to handle like the 1-year event, the higher average that's going to come in, and then they used a series of berms above the wall to handle that additional water capacity to reach that 100-year event. And so here you can see they're kind of grading it out. They're creating that depression. They're bringing in their drain rock. They've got the monitoring points already kind of set. They've already built the wall, but let me get into the wall construction here just a little bit. So about 2,500 square feet, 230 square meters of Allen Block Classics were used. We had a nice engineer on board, somebody that was very familiar with Allen Block and segmental retaining wall designs, kind of work with the site civil to make this happen. We love it when certified contractors get involved. These guys have gone through proper training. They understand why we do the things they do and why compaction is important and how water management comes into play. So we had second nature on the job site here. But what was interesting about this, I mentioned that they had to design the wall with a couple different phases or design phases in mind when it comes to water management. So like the first 5 courses, you can kind of see that being constructed here. Compaction was really tight because they wanted to make sure they minimized the differential settlement potential, because we know water will move things around. So they really concentrated on consolidating the rock. But you can see you almost have 5 courses of block that's going all the way around. And that gives them the capacity that they were looking for a certain percentage of that rainfall. And then I'll give you kind of the final shot. It's still kind of under construction here. They're bringing in the soil media, but you can see after the 5 courses, now they give you some overflow. They brought in some of the piping and stuff like that. You saw the one major pipe coming in on the one side here. But notice how they're constructing the berms above the wall. What I want to point out is they also have kind of an overflow point right here, which you see is similar to that same elevation of the berms. So if it does come up, they've got that overflow coming in. So again, getting into a lot of logistics when you're talking about bioretention ponds, because you got to look at the flow requirements or the water requirements. We just know retaining walls. Retaining walls, what we're doing is we're treating them as water applications, and we are trying to provide that usable land that you need. And that usable land in this case is giving them the space for that water capacity. And so that's really bioretention in Allen Block in a nutshell. And so if you look at this, we talked about that the bioretention ponds, their goal is to capture, treat, and store the water. They're trying to remove the water from the site in a slow and steady process. We know retaining walls are going to give the location meaning. It's going to define that space. It's going to help you satisfy the site requirements. And then it all boils into the best practices approach for water management, making sure we're doing everything we can to ensure water does not build up behind that wall. So we try to minimize the potential of having bioretention ponds above the wall. We want to get those located below the wall. And once they're below the wall, we need to know the high water mark, so that way you can know where your drain and your drain rock or your wall rock goes to with that fabric. So haven't seen any questions come in, but if you do have any, please fire them off at this time. I'm kind of wrapping it up. That's really all I had to present on that topic. I hope you found it of value, give you something to consider on your next project. I do want to encourage you to continue to participate in our online training opportunities. Our next scheduled monthly design professional is really a topic I think is going to be very interesting. It's kind of understanding ASTM standards, the C1372 for the block and grid testing. And what I'm hoping we can get into is a little bit more of how these blocks are made, maybe even show a little video. And so then get in the nuts and bolts of what it takes to make an Allen block. And so you guys get a better understanding of that. So that's April 23rd at our usual times. Central, it's 8, 10, 2, and 4 in the United States here. But then we were also asked, because of today's conditions and the fact that we aren't able to meet with as many engineers, because of what's going on in the world, we are offering daily presentations. In fact, the second handout that's part of this session you can download describes these 7 sessions in detail and even allows you to register for them. But while we're kind of cycling through these each day, like tomorrow, because we started these last week, tomorrow we're presenting GRS IBS applications and no fines concrete applications there. Then we're going to move into fence on Monday, and Tuesday we're doing above wall considerations, and then we're going to go back to the design presentation and best practices after that. But we're offering those 4 times daily, 11, 12, 1, and 2. Again, Central Time here in the States. But it's one of those where I hope you can participate. You'll notice that 6 out of those 7 do qualify for continuing education credits if you're interested in that. But it's just a small part that we are hoping we can bring value to you as we look to bring educational sessions during the little bit of a downtime that we have here. So I don't have any questions coming in. I'll leave this slide up in case anybody's writing this down. But with that, I'm just going to kind of thank you for your time. I'm going to just pause here momentarily to wish you guys the best. I want you guys to stay safe out there, and let us know how we can be a resource. I always tell designers we get to do retaining walls every single day. As fun as and exciting as that sounds, we like to think we get to pull from a lot of smart people out there, and we get to kind of come up with these answers that we know work. And so if you ever have a site problem and need to discuss it with us, please don't hesitate. Give us a call, shoot us an email, let us know how we can be that resource. We value that partnership, and we do look for future success as we move forward. So again, no questions I got. I do have a couple thank yous coming in, and I appreciate that. You guys have a great day. I'll stay on the line here for a couple more, for another minute, but feel free to log off, and I'm just going to kind of wait to see if any other questions come in. But again, appreciate your time. All right. No other questions. A couple more thank yous, and again, appreciate it. And we'll catch you guys soon.